everyone, welcome to part 2 of our lecture on chapter 15. Today we're going to continue with our talk on chemical equilibrium. Last time we were talking about our equilibrium constant K, and right at the very end of our lecture we were looking at how to manipulate K. We were looking at, okay, what do we do if the reaction is reversed or multiplied by a number or maybe added to another reaction, right? But all of these values for K that we were talking about last time, these are all in concentrations, right? If you'll remember, K was equal to the concentrations of the products over the reactants raised to the power of their coefficients. Well, today we're going to talk about equilibrium constants with respect to pressure, because sometimes we will do our reactions in an aqueous solution or just in a solution in general, right? We've dissolved our solutes and we will react them together. This is probably the most common in chemistry because it's easy to do on our bench, right? We just dissolve them up, mix them together, and our reaction goes. Sometimes, though, you'll do gas phase chemistry, and that's where Kp comes into play. So rather than just, I told you last time, we could say, sometimes we'll usually just use K, but sometimes you'll see it written as Kc, and I said that was for concentration. But usually if we just say K, we're talking about concentrations. If you're ever talking about pressures, though, then we will use this term Kp. So it's the same kind of thing. It's our equilibrium constant, but now instead of using, concentrations, we're using pressures. If we were to write our law of mass action for K, right, Kc to be specific, we would write our concentration of ammonia, NH3, squared, right, raised to the power of its coefficient, over our hydrogen cubed times our nitrogen. And we would have these brackets, right, because that tells us its concentration. Well, if you'll look at our term for Kp, we don't have any brackets. And I'm going to be picky on this, guys. Brackets mean concentrations. So if you have brackets, you mean concentration. If you put brackets in a Kp expression, you will be wrong because we don't have concentrations in our Kp expression, right? Because we're talking about pressures. Instead, we're using these P's with the subscripts, right? So this is like our partial pressure of ammonia, our partial pressure of nitrogen, and our partial pressure of hydrogen. And all of these partial pressures will be at equilibrium, just like all of these were our equilibrium concentrations. But otherwise, it's the exact same thing, where we're having our partial pressure of ammonia raised to the power of its coefficient over the partial pressure of nitrogen and the partial pressure of hydrogen raised to the power of its coefficient. You'll notice these are, reversed, but that's totally fine as long as they end up on, either the top or the bottom, just like they're supposed to. So it's exactly the same. You're doing this exactly the same way. The only difference is now, instead of writing concentrations, you're writing partial pressures. So here's an example. Here's our reaction. We have nitrogen and, our hydrogen reacting with ammonia. If we have our equilibrium pressures at a certain temperature, right, there we go. And so we can go through calculating Kp by plugging these equilibrium partial pressures into our Kp expression. So there's our law of mass action, and we'll just fill these in. We're just going to take them and fill them into our equation there. Okay, then you can go through and calculate it and find your value of Kp. Just the same as we did our equilibrium value of K. Now we're doing Kp, but again, these are just our partial pressures instead of our concentrations. Otherwise, all the same rules apply. If you flip the reaction, it'll be 1 over Kp. If you multiply the reaction by a number, it will be Kp raised to that, that power. All of the same rules apply to K and Kp. Again, we're just putting our partial pressures instead of our equilibrium concentrations. So if we are given K, we can solve for Kp and vice versa. And they're related by this equation here. Kp is equal to K times RT raised to the power of delta N. So delta N is going to be the sum of the coefficients of the gaseous products minus the sum of the coefficients of the gaseous reactants. Okay, so it's products minus reactants. But when you're looking at the reaction, sometimes you may have reactants or products that are in the solid phase, or maybe they're aqueous, or maybe they're a liquid. Okay, leave those out of this little equation, this, delta N equation. It's always going to be products minus reactants, but only the gases. And so we're looking at the coefficients of these gases, okay? And I have an example for you. Our R value is from our gas laws, 0.08206 liters atmospheres over moles Kelvin, or latim molk, as I like to say. And then our temperature is going to be in Kelvin. Okay, there's a big derivation we could go through. It's based on the ideal gas law, and we could go through and solve this, or you can trust me that this is the equation that you come out with. But that's why we're using this value here. It's from the ideal gas law. And then this is really important. Kp is equal to K when our change in our gaseous moles is equal to 0. So if we have the same number of gaseous moles on each side of the equation, then our change in our number of gaseous moles is equal to 0. So if this, if this is 0, anything to the 0 power equals 1. So that means that, this whole thing is just equal to 1. So Kp will be equal to K when delta N is equal to 0. Again, you're going to look at your coefficients. So if you add up all of the coefficients of your products, the gases, mind you, I'll add up all of the gaseous products, and then you're going to add up all the coefficients of the gaseous reactants. If your number there is the same, that means your delta N is equal to 0, and Kp will be equal to K. Otherwise, you go through and calculate it this way. Let's go through and look at it. So if we have the value of Kp for this problem, we calculated earlier, is 3.9 times 10 to the 4th. And I want to know, okay, if I know what Kp is, then what's K? Can I do this in concentrations, right? And so we have our equation, Kp is equal to K times RT to the delta N. Again, here's our Kp value given in the problem. Our R value is this whole thing, right? 0.08206 liters atmospheres over moles Kelvin. And then our temperature, right? We have 35 plus 273 to convert it to Kelvin. And then this is what I want to talk about here, this 2 minus 4. So again, products minus reactants. And the way that we do this, right, we look and we see, okay, all of them are gases. So we don't have to worry about, is one of them a gas or not. So our total coefficients on the product side is a 2. Okay, so right now we have delta N is equal to our products minus, and then we'll look at our reactants. So this is going to be 1 plus 3. So minus 1 plus 3, which is 4. So 2 minus 4 gives us negative 2. Okay, so that is our power that we're raising it to, our superscript here. So then you can go through and you can multiply, 0.08206 times 308 to the negative 2, and then divide that by both sides, and you'll get your K value. Okay, but this is the only part that people really find interesting or difficult sometimes, is this products minus reactants. Again, make sure you're only using the gaseous products and reactants. Okay. Heterogeneous equilibria. This is when, like I was alluding to before, that you have stuff in your reaction that is not in the same phase. Okay, so maybe, you're doing an aqueous reaction and you toss some solid in there. Okay, well, the solid is not in the same phase, especially if it doesn't dissolve, right? It's not in the same phase as your other reactants, right? And so this would be a heterogeneous equilibrium, where you have pure solids or pure liquids, or maybe you have gases and an aqueous solution, right? You just have things that are in different phases. What's important though here is that the concentrations of pure solids and pure liquids do not change during the course of a reaction, and this is because they're going to be in excess, right? And our pure solid, right? If it's a solid, is not dissolved, right? So our concentration doesn't change, because our solid is sitting as a solid. It's not dissolved. And same thing, our pure liquid is not dissolved in, say, water, right? So our concentrations of our pure solids and our pure liquids don't change during the course of a reaction. And since they don't change, we're not going to include them in our equilibrium expression, in our mass action expression, because they don't change. They're not going to affect the position of our equilibrium, so we don't need them in our equilibrium constant expression. Okay, so if we look at this reaction, we have carbon dioxide gas, we have water as a liquid, and we have our H plus and HCO3 minus. Okay, so the way that we would write this is we have everything that is not a pure solid or a pure liquid can go in our equilibrium expression. So we can have things that are aqueous, we can have things that are gases, but we can't have solids and we can't have liquids. Okay, so again, products over reactants. So we'll put our hydrogen and our bicarbonate on the top and our carbon dioxide on the bottom. There's no coefficients here, so we don't need to raise to the power of anything. We're just going to put products over reactants. But we won't include our water because it's a pure liquid and therefore its concentration isn't changing during the course of a reaction. So here's an example with a gas phase reaction, right? We have two gases that are present and they're reacting, one of them's reacting with a solid. Okay, if we look at these two different containers here, on the left-hand side, we have, a small amount of carbon, but on the right-hand side, we have a large amount of carbon. But our concentration, essentially, of our carbon doesn't change. The amount of our solid carbon is different, but our concentration of it didn't change because none of the carbon has, evaporated, essentially. So our concentration of carbon stayed zero both times, right? It doesn't change. And it doesn't matter because it's not affecting the position of the equilibrium. If you look, we have this different amounts of carbon on each side, but if you went through and counted all little molecules, we have the same amounts of carbon dioxide and carbon monoxide on each side, and it's at the same temperature. So we have the same value for K in each of these reactions, even though the amount of our solid carbon is different. Okay, our solid is not affecting the position of the equilibrium. Let's try an example. So here we are. We have PCl5 is making phosphorus trichloride and chlorine gas. And I want to know what is the equilibrium expression for this reaction. Okay, so remember, we are not going to include pure solids or pure liquids in our equilibrium expression. So the only thing that we can include is this chlorine gas. So remember, it's always going to be products over reactants, but in this case, there's no reactant, so we're just going to write our product. So our value for K is just equal to the concentration of chlorine. Remember, 3 dots, those mean therefore. If it's confusing to you, just go like that. So we have our K value is just equal to the concentration of chlorine because there's nothing else that we can include. We don't include pure solids, we don't include pure liquids. And our Kp expression would be just equal to the partial pressure of chlorine. Again, we can't include the solids, we can't include the liquids, so it's just going to be based on our chlorine. All right, we're going to change gears here and talk about what happens if we mess up our equilibrium, right? We talked about in the last lecture that, our initial rates are really fast, right? Our forward reaction is going really, really quickly. And, over time, our reverse reaction is kind of picking up speed until we get to a point where the, forward reaction and the reverse reaction have equal rates. That would be our dynamic equilibrium. So this is after that. Once a reaction is already at equilibrium, we've got our concentrations of our reactants and products are remaining constant because our rate of the forward reaction is equal to the rate of the reverse reaction. Okay, so everything's all fine and dandy. But now, what if I mess it up? What if I change the condition somehow? Well, what happens when you change the condition, maybe you've changed the temperature, maybe you've changed the pressure, maybe you added stuff, right? The concentrations of the chemicals in your reaction will change until the equilibrium has been restored, okay? It will find some new equilibrium. If it hasn't changed temperature, it will get back to where it equals the equilibrium constant again. If it's changed temperature, though, it may reach a completely different equilibrium, okay? But let's for now say that the temperature is remaining constant. So if I change the concentration of something, maybe I added some more reactants, well, the whole reaction will shift so that the equilibrium constant will be the same. It will start to make more products so that we can get back to that equilibrium, okay? The new concentrations will end up being different because you've added something. You've added maybe a reactant. So the new concentrations will all be different because there's more stuff in there, right? But if you went through and plugged it into the equilibrium expression, the equilibrium constant will be the same. Like I said, unless there's a change in temperature. But for now, since we're just looking at concentrations, let's talk about that. Okay, so this is called Le Chatelier's principle. He's French, so he has a funny name, but Le Chatelier's principle guides us in predicting the effect of various changes in conditions that they have on the position of the equilibrium. And it states that if we mess up our equilibrium, if we disturb our equilibrium, then the equilibrium will shift to minimize that disturbance. Okay, and we typically talk about it as shifting left or shifting right, or shifting towards the reactants or towards the products. And this is just telling us which reaction or which reaction will end up going faster. Will the forward reaction be faster to minimize this disturbance, or will the reverse reaction be faster to minimize this disturbance? But again, eventually it will get back to a new equilibrium, and then the rate of the forward reaction will equal the rate of the reverse reaction again. Okay, some of the disturbances that we can do, we can change concentrations of either reactants or products. We can change the volume, or we can change the pressure, which ends up being the same essentially, or we can change the temperature. So we're going to look at all three of these different types of changes, and a couple more too. Okay, so here's my analogy. We talked about country A and country B last time, right? We said that everybody lived in country A, and then they opened the gates and people moved to country B until they were moving, maybe 2 people moved from B to A, while 2 people moved from A to B, right? So our rates of our forward reaction and our reverse reaction were equal. 2 people were going and coming, which made our concentrations on each side of that wall constant, okay? Our rates, our forward and reverse rates were the same, so our concentrations stayed constant. So this would be our equilibrium. But now let's say people in country B started having a bunch of kids, right? Birth rate just totally increased. And now there were tons of people in country B. There's just tons of kids everywhere. Well, some of the people in country B are like, wow, okay, there are too many people over here now. I moved here because there was so much empty space. I liked my space. There weren't very many people. It was so crowded in A. I moved here to country B to kind of spread out. But now there's tons of people in country B. I don't want to live here anymore. There's too many people. So some of those people in country B now will move back to country A. Since country B is really crowded, right, the reverse reaction, right, the movement of country A is faster than the rate of people moving to country B. Nobody wants to live where all these people are, except maybe these are like grandparents or something, I don't know, right? But the majority of the people are moving to country A to kind of even it out. So our system is responding to our disturbance. Bunch of people over here increased the rate away from it, okay? And this will be true with our reactions as well. If we increase, say, the amounts of products, right, then our reverse reaction will end up going faster because it has a higher concentration. But eventually, again, this will all even out. And there will be maybe, equal numbers of people in country A and B, but at least, right, they don't have to be equal, but the rate of people moving into country A is going to be equal to the rate of people moving into country B. So Le Chatelier's principle states that when an equilibrium is placed under stress, which means that you've disturbed it in some way, right? You've added reactants, you've changed the temperature, something like that, the system will undergo a change in such a way as to relieve that stress and restore a state of equilibrium. Okay, so again, we're going to look at how does it do this. Here's a brief translation and kind of a more useful definition. If you take something away from a system in equilibrium, so say you're going to remove products or remove reactants, the system will shift to replace what you've taken away. Okay, so if I start to remove some product, then our system will shift to start making more product. Because remember, we had this equilibrium. And so if I went in and just pulled a bunch out, it's like, whoa, I've messed up the equilibrium. I need to make more solid to restore it. Okay. The opposite is also true. If you add something to a system at equilibrium, it will shift in such a way to use up what you've added. So say you added a bunch of reactant. Okay, well that way increased your concentration of reactant, and your system is like, whoa, too much reactant. Let's use it up and go make a bunch of product so that we can, come back to that state of equilibrium. Okay, so this is essentially what Le Chatelier means, especially in terms of concentration. So let's see how this plays out. Let's say we have a closed container of dinitrogen tetroxide and nitrogen dioxide, and it's at equilibrium. So here we are, and it's happy, it's at equilibrium. Our rate of our forward reaction is equal to our rate of our reverse reaction, but then I add some nitrogen dioxide. Okay, so now we're not going to be at equilibrium anymore because I've just dumped in a bunch of nitrogen dioxide. I way increased the concentration. And so what's going to happen is I've made this uneven, right? I've put in way more product than we had at our equilibrium. And so what happens, since I have a ton more product, our equilibrium is going to shift left to temporarily restore the equilibrium. This means that because we have a ton of product, our reverse reaction will end up being much faster than our forward reaction for a while because there's such a high concentration of product. So we need to use up some of that product to make more reactants so that we can reestablish our equilibrium. All right, let's look at another example. So if we have water and water vapor at equilibrium, so water, and then we add some energy, right? We heat it up and we can make water vapor. But what if I remove some of the vapor from the system? Okay, so again, I've affected this equilibrium. It was at equilibrium where, the water with the water vapor, right? Our liquid water versus our gaseous water, but I've removed water vapor. Well, now, again, your system is kind of out of whack, right? And so it will shift to make more water vapor to replace what was removed. So this means, because we've really decreased the concentration of our products, that will increase the rate of the forward reaction because like I said, we've messed up that equilibrium. We need to make more product so that we can reestablish our equilibrium. So it will temporarily shift right to restore that equilibrium. It's always going to shift toward whatever you remove and away from whatever you add. So here's it, in a picture form. So if we have, our dinitrogen tetroxide and nitrogen dioxide, and I add a bunch of nitrogen dioxide, just dumped in a bunch, well, that really increased our concentration of nitrogen dioxide. And like we talked about when we were looking at reaction rates, right? If we increase our concentration, that is going to increase the rate of the reaction. And here, since we increased this concentration, right, you can think of that as being our reactant. Essentially, it's our reactant in the reverse reaction. So since we increased that concentration, then it will increase the rate of that reaction. So it will increase the rate of the reverse reaction. This will cause the system to shift left to make more dinitrogen tetroxide. Okay, so when we add a reactant to a system at equilibrium, and it says as long as the added reactant is included in the equilibrium constant, okay? We will look at what happens if you add something that's not in your equilibrium expression next time. But for now, we're just going to say, okay, let's say we add a reactant to our system. And I want to know, how will that affect the rate of the forward reaction? How will it affect the rate of the reverse reaction? And how will it affect the value of K? So we're just adding a reactant. Our system was at equilibrium, adding a reactant, now what happens? Okay, so adding a reactant, right, if we think about this, we added a reactant. That will increase the rate of the forward reaction, okay? Because again, if we're looking at this, our reactants and products, if we increase the amount, our amount of reactants, that's going to, sorry, this should have been double-headed. If we increase our amount of reactants, that's going to shift it away from the reactants because we have to use up what we've added. Okay, so it will temporarily increase that rate of the forward reaction. But remember, when we were talking about rates of reactions, when we were writing these rate laws, it was always based on the amount of reactants. Had nothing to do with the products at all, right? So when we are looking at the rate of the reverse reaction, we haven't done anything to the products, right? Nothing has happened to them. So the rate of the reverse reaction hasn't changed at all because we haven't messed with the products at all. The only thing that's changed is the rate of the forward reaction because we've increased the concentration of reactants. And what will happen is the reaction will keep going to the right faster than it's going, than it's going to the left until we get to that equilibrium again. And then when we get to equilibrium, and this is, a little bit confusingly worded, so just kind of bear with me. At the new equilibrium position, you'll have more of the products than before, because remember, you added more reactant, so it's going to go and make a bunch of product, right? And you will have less of the non-added reactants before. So let's say we had some other reactants over here. Well, what happened is since I added a bunch of this reactant, and I made the reaction go this way, right? A bunch of this guy got used up to make more products, but I didn't add any more of that. So I'll actually end up with less of this other reactant than I initially had because it got used up to make more products. Okay, so that will be less of the non-added reactant, and then you'll have less of the added reactant again because, you added a bunch, it's going to get used up to make a bunch of product. Okay, you'll have less of the added reactant than you had when you added it, but more of it than before you added it. So there you go. There's your kind of word problem for the day. But at this equilibrium position, the concentrations of the reactants and products after we, get back to equilibrium will be such that the value of the equilibrium constant is the same. So if I plug all of these new, concentrations into our K expression, that K value will be the same before and after I added the reactant. Okay? That's the whole point of it calling the equilibrium constant. The only thing that can change that equilibrium constant is the temperature. So if you haven't changed the temperature, then the concentrations at equilibrium will always be the same. Well, sorry, the concentrations at equilibrium will always come out with the same equilibrium constant. My apologies. Okay, so that was what happens if I add a reactant. Similarly, if we remove a reactant, again, we need to make sure it's in the equilibrium expression. But if I remove a reactant, right, that will affect the rate of the forward reaction. And we can look at how it affects everything else. So if I, again, okay, let's write this out. We have reactants and products. And this time, like I said, I'm going to remove some reactant. Okay, if we think about this in terms of rates of reactions, if I remove some reactant, that means I am decreasing my concentration of reactants. That means the forward reaction will go slower, right? Again, this should make sense in terms of our rates of reactions. If I'm decreasing the concentration, my reaction rate will go slower. Again, it is not going to affect the rate of our reverse reaction because our rate of our reverse reaction is only based on the products. Okay, so our forward reaction rate will decrease where our reverse reaction rate will stay the same. So what ends up happening is that our reverse reaction rate is higher than our forward reaction rate just because the forward reaction is lower. Okay, nothing changed with the reverse reaction. It just happens to now be greater than the forward reaction because we decreased the rate of the forward reaction. Anyway, so what ends up happening is that our reaction will shift towards the reactants to go make more of it. Okay, our products will get used up at a greater rate to make more reactants, and so we will, and that will happen until we reach this new equilibrium. Okay. Once our rate of our forward reaction is equal to our rate of our reverse reaction, then we're back at equilibrium and all is well. Again, here's our riddle. At the new equilibrium position, you will have less of the products than before because what happened is that some of this product got used up to make more of the reactants. You will have more, like say that there was another reactant over here, you will have more of the non-removed reactant than you had before. Because again, our products are going to go make more reactants. We didn't take any of this away, so it just got, increased. We just made more of it. And then you will have more of the removed reactant than you had after you removed it, but less than before you removed it. So there you go on that one. Either way though, after this is all said and done, after we reestablish equilibrium, our products and our reactant concentrations, if I plug them back into that mass action expression, the equilibrium constant will be the same as long as I haven't changed the temperature. Okay? So, to sum up, If we add a reactant, that will decrease the amounts of the other reactants and then increase the amounts of the products until we get a new equilibrium position, okay? And again, we will have the same K. When we add a reactant, we will temporarily have a higher forward reaction rate, but we haven't messed with the reverse reaction rate at all. If I remove a product, okay, so we're removing a product, that will increase the amount of all the other products because it's going to shift to make more of those products, and it will decrease the amounts of the reactants. This is super useful, okay? So we will do this. Remember last time we were talking about values of K, and I said that if you have a reaction that has a really small value of K, then your reaction really isn't going very well, right? Your reaction, if it has a really small value of K, is still going to be mostly reactants until, once it reaches equilibrium. So the way that we can kind of force this reaction to go is to keep taking away the product. Because once you take away the product, the equilibrium has to shift to make more product. And so if we continually remove the product, then our reaction will keep trying to establish equilibrium by making more and more and more product. And so this is what it says here. You can use this to drive a reaction to completion. So if your reaction really isn't going, or maybe it's only going like 70% or 80%, and you want it to go further, then you can remove some of the product and it will cause the equilibrium to shift and make more product and drive that reaction to completion. Again, equilibriums will shift away from the side with added chemicals and toward the side with removed chemicals. Okay, and then again, if you add a solid or pure liquid, that's not going to change any of the concentrations, and it doesn't have any effect on the equilibrium whatsoever. So you could dump, like in that example, you could dump solid carbon in there all day long, and it's not going to change, your equilibrium whatsoever. Okay. So today, we looked at Kp, right, which is our equilibrium constant for pressures, and that had to do with all of the partial pressures of the gases instead of equilibrium concentrations of dissolved solids. We also looked at how Kp relates to K. We looked at heterogeneous equilibrium and talked about the fact that solids and liquids don't go in our K expressions. And then we spent a lot of time talking about CHATELIER'S principle and this idea of shifting our equilibrium left or right and disturbing our equilibrium, forcing it into a certain direction. We are going to talk more about CHATELIER'S principle in the next lecture. And we're going to look at, okay, what happens if I change the temperature? What happens if I change, the pressure or the volume? And so that's where we're going next. Make sure you're always working on those chapter 15 lecture worksheet problems. They're going to be really helpful in getting you used to talking about this shifting left and right and looking at, okay, what was removed or what was added and how does that affect our equilibrium? As always, while you're working, if you ever have any questions, please send them my way. I am happy to help you. All right, guys, I will talk to you all next time.